Hello everyone, these are my personal notes on the text for chapter 19. Remember, you can look under the week 5 questions thread in the My Notes post to find the Word document that appears here. So let's start with definitions. Population density is the number of individuals of a species per unit of area or volume of habitat. So we're talking about, like, if we look in one little valley, how many mice are there, per acre or whatever. That would be our population density. Age structure of a population. This is the distribution of individuals in different age groups. Reveals information that is not apparent in population density. For instance, age structure can provide insight into the history of the population's survival or reproductive success and how it relates in environmental factors. Thinking about human populations, you could look at different countries. What is the age? Is there a lot of young people, a lot of old people, a little bit of everything? What does that say about the country? It's the same can be true of different organisms in their population. Life tables. These track the survivorship, the chance of an individual in a given population of surviving at various ages. The life insurance industry uses life tables to predict how long, on average, a person of a given age will live, right? So think of, like, why would one person in a particular job, like a stuntman, maybe have to pay a heck of a lot more than, let's say, I can't think of a really easy job, a teacher, because that's really dangerous still sometimes, but something like that. A survivorship curve, you're going to see that down here. A survivorship curve is a plot of the number of individuals still alive at each age in the maximum lifespan. By using the percentage scale instead of actual ages on the x-axis, we can compare species with widely varying lifespans. And the population's pattern of survivorship is key to its life history, right? So if you look at, here's a couple of examples. Let's see. It's not going to show me. So if we look here, we have a picture of something, which I don't remember what the 3 thing is. We see, like, when they're young, there's a whole bunch of them, and not many people live out their full age. Lots of young, slowly declines, stays really good until you get pretty old. Dogs. Key life history traits include the age at first, reproduction, the frequency of reproduction, the number of offspring, and the amount of parental care given. So if you need to give more parental care, that's going to change what your life history looks like. If you need to give less. If you're going to reproduce all at once, my dogs are apparently ready to kill something. Are you going to reproduce all at once, like salmon? Or are you going to be more like humans where we just do it for a while? Let me pause for one moment. Okay, we will see if my dogs behave and stay outside. So many non-woody plants like dandelions produce thousands of tiny seeds, right? This is a very opportunistic life history. It enables the plant or animal to take advantage of favorable conditions, and general populations with this life history are the type 3 survivorship that we saw above, right? Lots of little babies, and I went too far. Lots of little babies, and then not everyone really makes it to the old age. I really scrolled up too high, right? Here's 3. So it looks kind of, we're going to call this looking more like a J curve. Not really, because the other way. Okay, lots of little, not much old. Then we have some organisms have an equilibrium life history, a pattern of developing and reaching sexual maturity slowly, producing few well cared for offspring. Organisms that have an equilibrium life history are typically larger bodied, longer lived species. Bears, elephants, and this is going to be more like humans, right? So you're pretty standard in the beginning, and then you drop off as you get older because you live for a longer period of time. So you're not just trying for everybody at once. Exponential growth patterns. This is when we get our shapes. I told you, Jay. Okay, exponential growth pattern describes expansion of a population in an ideal unlimited environment. In the exponential model, the population size of each new generation is calculated by multiplying the current population size by the constant factor that represents the number of births minus the number of deaths. Think of rabbits in Australia. They were introduced and they go crazy out of control. What do we do to control? How do we handle this, right? And since they're growing out of control because they don't have any predators. Exponential population is common in certain situations. For example, the disturbance such as a fire or flood, blah, 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 may suddenly reduce the size of a population. Organisms that have an opportunistic life history pattern can rapidly take advantage of this lack of competition and quickly recolonize the habitat by exponential population growth. Human activity can also be a major cause of disturbance. And plants and animals with opportunistic life histories traits commonly occupy road cuts, freshly cleared fields, and woodlots. Like, think about what you consider a weed. Is that going to be an animal that's more opportunistic, or the plant, or is that going to be something that takes longer to do? Poorly maintained lawns. However, no natural environment can sustain exponential growth indefinitely. Think about the deer in Grand Canyon when they killed off all the coyotes. It's going to look like a J, which we'll probably have a picture down here. Eventually an S. Environmental factors, these are called limiting factors. Limiting factors ultimately result in the number of individuals, restrict the number of individuals that can occupy a habitat because they're limiting, right? There's a carrying capacity. This is the maximum population size for a particular environment that can be sustained, right? Logistic population growth is the growth rate decreases as the population size approaches the carrying capacity. So once you get close to the maximum amount, it's just a slow little increase. When the population is at carrying capacity, the growth rate is 0 and looks like an S because it tops off at the top. Carrying capacity for populations vary depending on species and resources available in the habitat and just how often they reproduce. Passenger pigeons is a very good example of this because they still had a lot left when they were unable to reproduce anymore. That's not really carrying capacity. That's going to be your minimum required number. But you think about like whales, you probably have a different number that your environment can handle than like rats. Just different sizes, different amount of stuff they need to eat. So let's talk about stuff that gets in the way. Intra-specific competition is competition between individuals of the same species, because it's intra, for the same limited resources. Okay? So this is like males vying for females. A density-dependent factor is a population-limiting factor whose effect intensifies as the population increases density. So there's a famous space and rat experiment where the only thing limited was space, and the rats, like as more and more rats appeared because of reproduction, they got much more vicious toward each other because there's just too many of them. This intra-specific competition got super crazy, and that is an example of a density-dependent factor, because when there's not too many, no big deal. When there's a lot, it gets much more dramatic. Population limiting factor whose intensity is unrelated to the population density is called density independent factor. So it doesn't matter, it's always going to be a factor. So some populations of insects, birds, mammals undergo dramatic fluctuations in density with remarkable regularity. These are called booms and busts. During the population falls back to a minimal level, right? During the bust. The cycles of a snowshoe hare and lynx are your classic examples. Lynx is one of the main predator. Every 10 years, both hare and lynx populations show a rapid increase followed by a sharp decline. What causes these boom and bust cycles? Since ups and downs in population seem to almost match each other in the graph, does this mean the changes in one directly affect the other? So basically, if you're going to have a bunch of rabbits, pretty soon a bunch of lynxes are going to show up to eat them. This is going to decrease your rabbits while your lynx increase. Then there's not going to be any more hares around, so that's going to have a lot of death in the lynxes, which leads to an increase of hares, right? This is considered an arms race. We talked about arms race yet? We will if we haven't. I feel like we already talked about it. It's fascinating stuff. U.S. Endangered Species Act defines endangered species as one that is in danger of extinction throughout all or a significant portion of its range. Threatened species are defined as those that are likely to become endangered in the foreseeable future. Okay, so we have to decide which animals do we save, which do we consider worthy of saving. As an environmentalist stance, we usually try to think of like there's species that you could pour money into and you're not going to be able to save them. There are species that just need a little help, and there are species that are probably going to do okay on their own. So we tend to try to focus on that middle segment because you're a little bit of effort is going to go a long way. And there's some species, well, sadly, you're probably just going to have to let them die off. Looks like the rhinos are going to be one of those. So sustainability, we talked about that, being able to use resources, and then there's a nice definition here at EPA. What is an invasive species? We've been talking about this, but let's actually define it. This is a non-native species that has spread far beyond the original point of introduction and causes environmental or economic damage by colonizing, dominating suitable habitats. The examples are kudzu, zebra mussels. You might have local invasives. Hawaii has a whole strategy to try to control this. Let's see. They're talking about an invasive plant in the western U.S. It's called cheatgrass, and it has taken over where the native grass used to be. And it says it shows up before the native grasses are able to repopulate, and this is able to outcompete. Usually there's some type of thing like that, like they can get in there faster, but they have traits in a similar environment that were evolved, right? Which I'd love to think of the name right now. Correlated's wrong. I'll think of it later and be like, ugh. But anyways, they have those traits, and so when they're plunked into their non-native environment, they're able to take control since they don't have the natural predators that the native grasses would. So let's look at biological control. This is the intentional release of the natural enemy to attack a pest population. This can be really bad though, because you're hoping that the enemy, the predator of this new pest, is still going to go after the pest once you've released it. Sometimes the predator decides to go after something else and becomes an even bigger problem. So I said biocontrols go wrong. There's a good example in Hawaii. Let you look it up. In the 1840s, a protist that caused a disease called the potato rot wiped out the entire potato crop of Ireland in just a few years. I believe, because I just read about this, that it actually came from South America, and it led to the Great Famine. It was a huge issue since, of course, that's the Great Potato Famine, right? And the English kind of blamed the Irish for just being dirty, and they didn't really help them out. So Ireland is still recuperating its population since either died or left. Insane. Really fascinating history if you ever get a chance. Plant-eating insects can cause massive damage. That's also would be like the Dutch elm disease. What synthetic herbicides and insecticides such as DDT were developed in the 1940s, right? So we thought, oh yay, this is like the perfect thing. Unfortunately, the chemical solutions to pest problems bring numerous problems of their own. These chemicals are pollutants that can get carried great distances by air and water currents. DDT itself never breaks down. Some countries still use it, but it stays in the water, so it can be in the dirt, just hanging out. You have a really heavy rain, it finally leaches out of the dirt, and you're back to the environmental problems. This is a chemical that causes very thin eggshells in things like pelicans and eagles, and really led to a lot of death of protected species. Integrated pest management, IPM, uses a combination of biological, chemical, and cultural methods for sustainable control of agricultural pests. Researchers are also investigating IPM approaches to invasive species. So you just really have to try to do this without effing stuff up. Let's see how much more we have on chapter 19. Oh, I think we can actually maybe in a minute finish it. Let me pause for a sec. So basically this all goes into like how human growth rate is really causing a problem. We have not leveled off and made our S curve yet. I think that's predicted to happen in like 2050, something like that. It's just recently did a statistical study. But this is a really great video that shows you with lights where the human population became really present. So if you get a chance, check it out. It's just fascinating. Oops. Checkpoint. Okay, so the situation which results from increased proportion of women of childbearing age in a population is known as population momentum. Girls 0 to 14 and 85 are in their reproductive prime in 2010, right? And then those that are 0 to 14 in 2010 will carry the legacy of rapid growth. So it takes a lot of effort to control that. An ecological footprint is going to be what resources you use and how that affects the environment. I've got like 10 seconds, and that is it for chapter 19. I hope you enjoy this. I hope it helped just shed some light.